The electronics industry faces a serious challenge in reflow soldering fine pitch surface mount components. Recently, solder paste application equipment has become more accurate and repeatable due to the implementation of automatic optical alignment and laser inspection. Improvements in paste formulations have allowed for substantially better resolution, tack, and reflow properties. Yet even with these improvements, the limitations of current technologies are becoming evident as densities increase. Nearly 2/3 of all SMT process-related defects can be attributed to poor solder paste printing. Inconsistent deposit thickness, paste buildup on the stencil, and Z forces at placement all contribute to both shorts and opens during reflow. The volatile reaction during reflow causes the formation of solder balls and can entrap flux and activators, producing inferior electrical, thermal, and mechanical contacts. Environmental regulations associated with the handling, storage, and disposal of solder paste and stencil cleaning materials and chemicals put additional burdens on the electronic assembler. Aggressive reductions in component lead pitch and rapidly increasing surface mount densities require a new approach to solder depositions. Precision Pad Technology, or PPT, for which a patent application has been allowed, was developed to address these issues and increase first-pass yields through assembly. PPT is an enabling technology which dramatically improves fine-pitch solderability by applying a solid reflowed solder deposit to each surface mount land on the bare printed circuit board. The macroplanar deposit is of sufficient volume to provide high-quality solder joints at assembly. This technology eliminates the requirement for solder paste application prior to component placement. Adhesion of the components at placement is achieved through the application of a tack flux. The flux can be of a mildly active, no-clean variety, which eliminates the need for cleaning the finished assembly. Precision Pad Technology consists of the following steps. A. Application of solder paste. B. Simultaneous reflow and planarization. C. Cleaning. The application of the solder paste is achieved by stencil printing, typically using a 4mm stencil imaged 1:1 with the copper surface mount lands. Solder thickness is controlled through both the solder mask and the stencil thickness. Normal considerations in stencil printing, such as registration and resolution, are not as critical in the PPT process. Printed shorts and misregistration, which can produce fatal defects in the conventional assembly process, produce high-quality solid solder deposits when PPT processed. Block printing on fine pitchland patterns eliminates the stencil clogging normally apparent when printing through small apertures. After solder paste application, the boards are sent to the RPU, reflow and planarization unit. The RPU is a computer-controlled robotic reflow system constructed of extruded aluminum alloy and stainless steel. All electronic systems are housed and monitored in the isolated control module. Main power, blower, heater, and exhaust are controlled via the high voltage panel. Blower air velocity is indicated on an LED display. Heater temperature read and set points can be viewed and adjusted on an LCD display. Start, spacing, stroke, and speed settings are all adjusted via thumb wheels. Vibration volume is infinitely adjustable via a potentiometer. Motion status, LEDs, allow the operator to easily monitor robotic movements. All motion is controlled by a 486 computer and indexer electronics. Cycle start commands are initiated via the Windows-based control panel or by tandem cycle start switches housed on the RPU. Motor positions, directions, and limit status are displayed in their own respective windows. Printed boards are shuttled into the unit on the lower table, which uses hard tooling to shim and register printed circuit boards. Once the table enters the RPU, the upper table housing a tension stainless steel mesh is lowered onto the boards while vibrating. The mesh sifts through the solder balls in the paste deposits and comes to rest on the permanent solder mask, creating separate reflow planes. Robotic actuators move a 40 kilowatt heat source with a 24-inch nozzle into position over the substrates. High velocity hot air is forced through the mesh and onto the substrate. the solder paste deposits reflow and something truly unique happens. Excess solder paste is allowed to pass up through the mesh. Shorted solder paste deposits are prevented from forming reflowed shorts and either pass up through the mesh or follow the strands of mesh back to their respective pads. The mesh allows for the necessary balance between isolation and connectivity of the solder balls to force the reflowed solder to its desired locations. This technique also produces a highly desirable reflowed solder surface for the application of attack flux and component placement. The reflowed solder deposits are macroplanar with an embossed surface topography which retains a high volume of tack flux. After reflow, the solder deposits are quenched with a lower temperature cooling pass by the heat source as it returns to its home position. High temperature air is exhausted in the home position by a highly reliable air amplifier, which has no moving parts. Excess reflected heat is exhausted through the same air amplifier by a manifold surrounding the upper table while boards are being processed. Any residual heat finds its way to an additional air amplifier located in the exhaust hood. After the cooling pass has been accomplished, the upper table is again raised, and the lower table with planarized boards exits the RPU. As the lower table approaches its end stop, the circuit boards are again quenched, this time with ambient temperature air, supplied by an air knife. The large surface area that can be processed per cycle, a full 24 by 28 inches, permits high volume production. The integrated scales allow for fast, accurate setups, optimizing productivity. After reflow, the boards are cleaned, using conventional cleaning equipment to remove any flux residues and solder balls formed when planarized. Residue removal is much less difficult without components obstructing spray patterns. Inspection of solder deposits on the bare board confirms that every surface mount land on every board processed will have sufficient solder to form a good quality solder joint at assembly. PPT-generated solid solder deposits have been demonstrated to produce higher quality solder joints after components are reflowed. Precision pad technology has dramatically increased the operating window when soldering fine-pitch surface mount components. PPT-produced solid solder deposits eliminate shorts and solder balls at assembly. Encapsulating copper lands in a thick solder deposit with a single thermal excursion increases bare board shelf life. Increased yields enable the electronic assembler to be more competitive in an increasingly competitive global market. Your assembly solution has arrived.